the fiber. Previously, we looked at a fiber optic where we have the cladding and the core. And we realize that as light enters the core, it has to be at a certain angle for total internal reflections to occur. So for single mode fiber, this is too small that only one light is passed through the fiber, making it single mode. As for multi-mode, this is big, that many light pulses can pass through, creating multiple transmissions. So for today, we shall be looking at mainly single mode. And single mode, first of all, let's define dispersion. Dispersion is the broadening of transmission signal light pulses as it passes through a media. Let's take this to be our fiber optic. As a signal, a perfect signal is transmitted through the fiber optic. It is received as this kind of pulse. There's this broadening. So the pulse is broadened as it passes through the fiber optic. Under dispersion, we are going to look at different aspects of dispersion. We have material, waveguide, and chromatic. So under material, we shall consider this prism. As light passes through, white light passes through the prism. Remember, a prism has a refractive index, and the refractive index is wavelength dependent. Now, as it passes, this white light, as it passes through the prism, it will have different wavelengths, because as light is emitted, no matter how narrow the light is, it always emits several wavelengths. So as these different wavelengths meet the medium, they are dispersed at different velocities. And that is how we see the output of the transmission through a prism. So if we are to call the material to be of dispersion dm, then dm, magnitude of it, is we notice that it is wavelength dependent from the formula change in tau, whereby this is representing the extent of pulse broadening divided by the length of the fiber optic, and times the change in what we may call as the spectrum. So what we have to notice here is that dispersion is fixed. In other words, we cannot change the dispersion. However, when we look at the waveguide, we have the core, and then we have the cladding, and the whole of this is the fiber optic. So the difference comes here in the waveguide as the guide having different refractive indices. The core has a different refractive index, and the cladding has a different refractive index. So with those different refractive indices, we realize that there will be different wavelengths. So if you want to change the dispersion within a waveguide, you basically have to change the design of the fiber, and that is how you can change the dispersion. So we shall take waveguide as DW. Now when we are to look at chromatic, let's call it DCH. Now for chromatic is the summation of DM and DW. If we are to look at its graph of dispersion against the wavelength, we notice that as the wave passes through the waveguide, there is a reduction. dW. Then through the material, there is an increase in dm. So at this point, we have to note that there is no dispersion taking place. Then a chromatic gives us this, which is DCH. So we can call DCH as total dispersion. Let's look at chromatic or total dispersion in simple terms. Assume you have two bodies, body A, body B. Body A is moving at 100 kilometers per hour and body B is moving at 80 kilometers per hour. After a certain time, body A will be a little in front of body B. Then, after a total longer time, body A will be far ahead of body B. So if we were to look at the time difference between the first scenario and the second scenario, we notice a big difference in the second scenario. Here, what it tries to mean is that the longer the distance, the more time difference between the two bodies. That is basically how chromatic dispersion works. Looking at the effect of total dispersion, we assume this is our fiber optic with a perfect input signal. There will be broadening of the light pulse. So this is transmitted and this is received signal. So there is a pulse broadening. Then the second effect is that if this is our fiber, if two perfect signals pass through, or as many as possible, are transmitted through the optic fiber, this is what we shall see. There will be an overlap, creating what we call bit error.